Hey guys, welcome to my adventure in technology and perhaps yours as well. This is probability and statistics, and since it's been a little trouble getting this up, we're not going to make this overly long, but we're going to start off right off the bat with some basic questions. If I let 1 represent heads and 0 represent tails, and there are 4 scenarios here, A, B, C, and D. It's a list of 10 ones and zeros. Could ask the following question. Which one is most likely someone having rolled a die, and which one is a human pretending to be a die? One of the big problems with probability and statistics is humans don't actually naturally understand what it means to be random. In fact, we're going to discover that your intuition sometimes will fail you, as does mine, because we have to be very careful. If we kind of look at these, we might look at the characteristics of these 10. There's 1, 2, 3, 4, 5. This has 4 zeros and 6 ones. This one's got 1, 2, 3, 4, 6 zeros and 4 ones. This got 6 ones and 4 zeros, and this one's got 9 ones and 1 0. And so it seems that this 6 4 6 4 is pretty common. But if I was to look at these, I would tell you that there's 2 of them here that I'm asking a human to be random kind of stick out to me. And these are both B and D. And the reason for this is in both cases there's this fairly long string of something. Humans seem to have an intuition that thinks when you're rolling a die or flipping a coin that this happens quite frequently, that they seem to go back and forth. There's no strings of zeros and ones. Now this one's very interesting. There's 2 strings of zeros and 2 strings of ones. We call these runs, and runs are actually very common in probability. However, it's not really a good measure of a human did it or not, but if I were looking at this, if I was told these are all human, except for 1 randomly flipped one, I would have picked B as the randomly flipped one with a fair coin, and would have assumed the others were human. In fact, I would have said, oh, here's a kid trying to outsmart me. If I had to say, nope, that was wrong, then I would have gone to this one second, because I don't think humans like to think that way, that that's the way a coin flips. So what is probability? Statistics is very simple. It's measuring things, and it's telling you averages and stuff, and we'll talk a lot about descriptive statistics as we go along. In fact, descriptive statistics, average, mean, mode, things like that. We'll define them, we'll go through them. If you haven't had a statistics course, we'll make sure the descriptive statistics are in your hands and you're able to use them and understand what they mean. But the idea of the probability of something is we want to understand. So, what we're going to begin with is explain that the concept of random, first off, it is locally unpredictable. This is really important to understand. If you roll a die, let's say we're interested in 1 and 2 as a win, for whatever reason, we've got some game going, and 3, 4, 5, and 6 is a loss. Well, I want you to notice the probability of a win. You should be able to see that there's 2 ways to win out of 6 ways to roll a die. We'll define this very clearly later. 2 6, 4 6. Why, it looks like you lose much more often than you're going to win when you play this game, where 1 and 2 is called a win, and 3, 4, 5, and 6 is called a loss. Those probabilities, winning is less likely than losing, yet this is a very reasonable probability situation. But is it fair? Should you lose more often than you win? So this you shake, it's locally It's long-term predictable. This is a consequence of how we're going to define probability. Randomness causes local unpredictability, but long-term predictability. So when we create a model of something, and we expect that model to make sense, a probability model, over a long enough period of time, we should be able to understand if our model's working well, because it should be long-term predictable. So, let's look at this D here and see how you interpret the idea of long-term predictable. D was 9 ones which were heads and a tail. Now, that doesn't look like really random, but if it is a head or a tail, and we expect half to be tails and half to be heads, then what do you think's going to happen next? Are we going to get more ones and zeros? Well, how can we possibly get more zeros to catch up to the ones that had too many? Because at any point, wouldn't you would say we expect half ones and half zeros? So how in the world can we make up for all those ones that were there in the first place? In fact, we're not expecting to make up the ones. Well, we're expecting over a long enough period of time that there's going to be about half ones and zeros. So let's demonstrate this. Let's take those 9 ones and a 0, and let's follow it by 10 more shakes. But amongst those 10 shakes, let's make it really even. 5 ones, 5 zeros. I don't care which order. Now I want you to notice. 1 was tails. I want you to notice that in the first 10 shakes, we were 90% heads. Sorry, 1 was heads. And we were 10% tails. Now, we picked up and did 10 more. And we were 50-50 heads and tails. But look at what has happened now. We now have 9, 5, we have 14 heads. And we have 6 tails. And now we're at 70% heads and 30% tails. We're catching up. Let's keep going. Let's do it for 50 more times. And let's say it's like, say, 26 ones and 24 zeros. Again, ones are dominating, right? But not by much. What's happened now? Well, now we're getting really far out there. 50, 60, 70 times. Let's count up the ones. 9, 14, 30. And since we've done 70, now we have 50, 60, 70. I think I added wrong. 9, 14, 30, that's 40 ones. And the zeros are 1, 6, 24, 30 zeros. And so now we're 40 70ths heads, and we're 30 70th tails. And guess what? Both of these numbers are getting closer and closer to 50%. Now, some of you may have memorized what division by 7 does. It's a very unique fraction. It is a rotating fraction, so that you, some of you may know these exact values. But here's the cool thing. You're catching up on on tails, without actually shaking more tails. You still actually shaking more heads, but you're catching up in the percentage. This is what we mean as a long-term predictable. That's how we expect dice to behave. Now, what model will allow us to do this? So you've been doing a lot of this. You create models. Models have 3 important characteristics. First, is we usually like to make pictures. Believe it or not, we're going to draw pictures as much as possible. We like to minimize the use of variables, but we want equations or functions with variables. What else do we want with a model? We want characteristics of a problem, the least number of characteristics that define something well. So saying that something's random, well, it's not quite enough. I mean, we can randomly draw a card from a deck, we can randomly shake a die, we can randomly cut a log and measure how long it is. I mean, there's lots of things that constitute random, so what are the characteristics we're looking for is really interesting. Now, before we start doing lots of models, we first need to understand what we want probability from a model to mean. So a very simple probability needs to have a function that somehow measures the probability of something. So we usually write P of x. That means we need to know the domain of x. So for example, I'm going to give you a probability function for shaking a die. P of x equals 1/6, x equals 1, 2, 3, 4, 5, 6. Now that's kind of a boring function. However, it looks like this. How do I represent? Should I use dots? Yeah, I'm going to do it that way. Here's 1, 1/6, 2, 1/6, 3, 1/6, 4, 1/6, 5, 1/6, 6, 1/6. That's one way to draw it. I really like to draw them this way. Like to draw it as a bar graph, and I don't like this so much, but so be it. So we have a function called a probability function. Oops, got to remember to let you guys see the things. We have a probability function, and we have a couple ways of representing it. We have a domain. So is this a legitimate probability? I think you're comfortable with that's how dice work, but what really makes it a probability? Well, we need a definition. Probability function. Well, first off, when we have a domain of that, I want to define probabilities so that the probabilities are always positive. Why? Well, I don't know what a -1/3 probability would mean. It doesn't seem to be a good thing. So I think I like it this way. Next thing, it's okay for something to have probability 0. This is absolutely fine. It just means it doesn't happen or is impossible. Well, we'll learn through time what it means, but it's okay to have that happen. Now, the other thing is we want the probabilities to be less than or equal to 1. So we can think of probabilities as a percentage. 100% like gotta happen. So it's okay. Probability of 1 is all right. Now, what happens if two things are disjoint? They have nothing to do with each other. And we want to find the probability of x1 or x2. And x1 and x2 have nothing to do with each other. Well, we would like to be able to add these probabilities. But we have to be very careful. We don't want x1 and x2 to be affected by each other. They're just a distinct event. And lastly, if we look at every single probability, if the union of all of these is the all events, then the probability of x1 or x2 up to xn, it should be 1. all probabilities add up to 1. Things that have nothing to do with each other can't affect each other than the probability of one or the other is the sum of the two probabilities. And zeros and ones are okay. This seems to be a very valid definition of a probability function. Now, let's draw a picture. Why? Because pictures rock when it comes to certain problems. So, let's suppose this is a universe, and we've got people in this universe. Let's make them athletes and chess players. So, by drawing it this way, I have a set called A, and I have a set called C, which are the chess players. What does this picture indicate? Well, this picture indicates that there are people in our universe. Some are athletes, some play chess, some do both, some do neither. So what this picture contains is it contains A, contains C, contains A intersects C, that's this. It contains A union C, that's all of this. And it contains the things outside of A union C complement, sometimes just called prime, and sometimes written this way. There are several ways that we write complement. You need to understand that complementation, however, is an important idea. Complementation is with respect to the universe. You have to know the universe in order to know what's not in a set. So, we can draw pictures of these things. What's really interesting is there is even more spaces in here we haven't identified. For example, how would we identify this place? That's the non-athletes who are chess players. How can I write this in set theory notation? They're not an athlete, and they're a chess player. So, and, isn't that how we usually can think of intersection? The English word and the English word or is the union. Now, warning, the English word or varies. You ask somebody, dinner or a movie? And they go, sure, both. That's the mathematician's or. Completely allowed that an or you can do both, not an exclusive or. So computer scientists have XORs or exclusive ORs. Our or is one from one set, or it's in the other set, or maybe it's in both. So I think that we can define this as not an athlete and a chess player. Now there's another one in here. What's that one? Well, that's not a chess player and an athlete. And this one, boy, that was A intersects C. And the stuff outside, that was this one. It looks like there's lots of things that we can be talking about in a picture. Oh my goodness. Now, if we're going to use set theory, then we're going to want to make sure that we understand what these things mean. For example, what's it mean for two sets to be equal to each other? Well, first off, the meaning of this, every element of A is in B as well. In other words, A is a subset of B. And every element of B is in A as well, or B is a subset of A. This is how we actually prove two sets are equal. Got to be very careful there. So we're going to write things like let A be an element of A not an element of B. Well, what's this mean? Well, A's not in B. That means A is an element of B complement, and A is an element of A. So A is an element of B complement and A. So this says this. So we're going to interchangeably work with how to write things and how to express them and go back and forth. Got to be careful about that. I'm not going to be too picky. Math 200 takes care of that massive pickiness. All right, so these diagrams that we draw with a universe and athletes and chess players, I can actually put some people here. So I'm going to do a count. Ready? I'm going to look at athletes and chess players at Augustana College. I'm going to start with a universe of 2,110 people. And I'm going to claim that there are 700 athletes. I'm going to put 690 here, 10 here, and 85 here. Now I want you to notice that I have 95, and we write it this way. The cardinality of C is 95. Cardinality of A is 700. Cardinality of the universe, 2,110. There's one number missing out here. Those are the people outside. How many is that going to be? Well, these four numbers have to add up to 2,110. So, A union C prime size, well, we've got the 95 and the 690 plus something else should be 2110, so that something else is what we're looking for. So A union C complements order should be 2110 minus 690 minus 95. So this is 2. I'm having trouble adding. Here we go. 6, 7, 85. So 2, 11, 10 minus 7, 85. What is that? 14, 13, 25. Huh. That's kind of interesting. We can delete almost any one of these numbers and be able to do a calculation. However, let's now talk about probability. This is a Venn diagram with raw numbers. I'd like to make a probability Venn diagram. Let's suppose in this universe we'd like to say everything is equitably likely. In other words, you can't reach in there and pick the best chess player just automatically or the tallest. Maybe we have a famous basketball player, and when you think of an athlete, you pick that person. No, let's make it what we call equitably probable. In other words, you reach in and grab one, you have a likelihood is how big of the set over everything. Well, I want you to notice, then I can say the probability of an athlete, well, would be 700 over 2,110. I can say the probability of an athlete and it's not a chess player will be 690 over 2,110. And I can say the probability of a chess player and not an athlete will be 85 out of 2110. So I can take each one of these numbers and I can divide by 2110, and I will get what's called a probability Venn diagram. And these are now probabilities of events. An equitably probability, or equally likely, is like drawing cards from a deck of cards, picking people from a room. We're saying everything is equitably likely, and we like to put them in Venn diagrams. Now, when we do that, something interesting happens. What is the probability of A or C? Well, remember when I said the probability of x1 and the probability of x2, if they have nothing to do with each other, should be their sum? I'd like this to be P of A plus B of C. But it's just not. Because if you add up P of A, you get 690 over 210 plus 10 over 10. And add in P of C, you get 10 over 2110 plus 85 over 2110. You've added this one twice. And you have to subtract off the probability of A and C. And this is our first fundamental fact using sets and probability theory, the relationship between the and the or and the sum. Now the book's got A and B. I like using A and C. Mix it up. Now, the next fundamental fact is, suppose we just look at one of the sets. This is 0.70 for athletes. What's the probability of a not athlete? Well, if the probability of A added to the probability of not A, well, that has to be everything, 1. So we now have the complementary law. The probability of a complement is 1 minus the probability of original problem. This complementary law is a very powerful thing that we're going to use. I will frequently calculate something by a complementary law because it's easier than a direct computation. Now, there's something else. We love our pictures. So, I'm going to draw a classic picture. This will be the last thing we're going to look at. It's called a tree. A tree has a starting point, often called a root, and then you move forward as things progress. So let's suppose we launch a rocket, and here's a success. Uh-oh, here's a failure. It blew up. We're not going to do anything with that after that. Blew up. But if we have a successful launch, then we might do it another time. So now we're going to launch again, and here's another success, and here's, uh-oh, a failure. And after it blows up, we can't do it again, but success, we can launch it again, followed by a failure. Launch again, followed by a failure. So if you're a model rocketeer, you want to go down this one, because when it blows up and you lose your rocket, or real life, this can go on forever. So this tree can be infinitely deep. Ooh. What happens, we're talking the probability of specific launches being a success? Well, a success at launch x equals 12. Oh my goodness. Starts getting a hard question. That means you've had 11 successful launches. Is that different than asking the question is, what's the probability of 12 successes in a row? Is it different to say probability of success at launch equals 12 versus the probability of 12 successes in a row? And the answer is, in English, yes. This one has prior information. Prior. This one does not. If you're at root, what's the probability of making it to 12 successful launches? Versus, if you're at the 11th success, what's your probability for the next launch? Well, maybe it's the same as the first launch. You work it out, you work on it. Maybe each launch is independent of each other. I'm not sure. This is an interesting problem. Interesting questions start arising under repetitive actions. All right. There's our first one. We'll rip it and go from here.